last time we started studying three codes, Walsh-Hadamard, and we showed that the distance is half. Next we studied Reed-Solomon code, which is the most famous code. We showed that the distance is in the non-binary alphabet, it is very close to 1. Okay, but remember that this is not binary. If it was binary, then the distance would have been half or less, but this is close to 1 because of non-binary. Then we looked at the multivariate generalization of Reed-Solomon, which is called Reed-Muller code, and that has similar distance, which is 1 minus d over the size of the field, okay, where d is the degree of the multivariate polynomial. So, next we will use both of these, Reed-Solomon and Walsh-Hadamard, and give a code that has the advantages of Reed-Solomon, but it is binary. So, these are called concatenated codes. And these are also old, first given by Forney in 66. So, Walsh-Hadamard is very good distance wise, it is also binary, but the problem is it is very long, right. So, Walsh-Hadamard has a large length m, while Reed-Solomon uses a non-binary alphabet. Reed-Solomon you cannot do for binary alphabet because it needs a field and the field has to be big enough. So, Walsh-Hadamard has the problem of large m, Reed-Solomon requires non-binary alphabet. We want to solve both the problems, the solution will be via concatenation. Both the drawbacks. Okay, we want to remove both the drawbacks. So, what we do is we first apply Reed-Solomon, and then we apply on the non-binary alphabet these field elements, we apply the Walsh-Hadamard code. Okay, we need to apply Walsh-Hadamard on these field elements so that any change in the field element should spread around the bits. So, let us define this formally. Okay, so Reed-Solomon will spread it across field elements, and then Walsh-Hadamard will spread it across the bits. So, let f be a finite field right, finite alphabet of size q. Reed-Solomon is the map on n length message in this f alphabet, it stretches it to f to the m. And Walsh-Hadamard, this will stretch a field element viewed as binary. So, 0 1 to log q. So, actually what this is, let me first write fq. So, view f as binary space log q bits, and then Walsh-Hadamard you know is exponential, so it will stretch log q to q. So, the concatenated code Walsh-Hadamard, Reed-Solomon this is the map which views fq to the n as 0 1 to the n log q and maps it to. So, first fq to the n is mapped to, or we are calling it f. First this f to the n is mapped to f to the m, and then f is mapped to a longer string which is q long. So, you get qm. Okay. And how is it mapping? So, view Reed-Solomon as a code from 0 1 to, so first maybe I should write it like this. In the first step what Reed-Solomon will do is it will give you the first field element, second field element, and the mth. Basically, on a string x, which is an n tuple of field elements, it will stretch to m field elements. So, this is in f to the m. And in the second step, it will apply Walsh-Hadamard on each of these field elements. Okay, so the ith symbol view it as a Boolean string, and then Walsh-Hadamard will stretch it further. So, you will get each symbol will be mapped to 0 1 to the q, and the whole thing is, this whole thing is then in 0 1 to the mq. Okay, so this is the definition. This is how Walsh-Hadamard Reed-Solomon concatenated code acts. So, you know that Reed-Solomon is an efficient code, efficient in the sense of poly m log q, and Walsh-Hadamard will take time poly q. So, overall this is polynomial in m and q, and m is also comparable to field size. So, you can observe that Walsh-Hadamard Reed-Solomon is computable in poly mq, which is equal to poly field size. It is completely polynomial time, deterministic polynomial time computable. Now, what is the distance? Right. So, last time we did lemma 3, which was distance for Reed-Muller. Let us now repeat a similar analysis for concatenated code. Let us call it lemma 4. So, Walsh-Hadamard Reed-Solomon is an error correcting code of distance. So, Reed-Solomon code has distance 1 minus n minus 1 by m. right? So, two different strings or two different n tuples from the field will be mapped to tuples which are m tuples, and they differ in uh, these many places. In those places, Walsh-Hadamard will, when you look at the binary representation, Walsh-Hadamard will differ in half of the places. So, it is actually product. Okay, this is the distance. It is product of the distance. So, the proof is quite straightforward. Let x and y be basically n tuples from the field which you are now viewing as binary string. So, we know that number of distinct elements in Reed-Solomon encoding of x and Reed-Solomon encoding of y is, this number is 1 minus n minus 1 by m times m, right, distance times the stretch length, the code word length. In these many places RSX and RSY differ. Moreover, if x prime y prime field elements are in the ith place, of RSX, RSY respectively, then in the Walsh-Hadamard stretch or encoding, the distance is half. Right, this means that overall, if you look at the binary distance between the concatenated code of for x and that for y, this is the places in where you get difference in the Reed-Solomon level is this, and the places amongst these, now when you apply Walsh-Hadamard, the differences is in half times q places, and the total length in the end is mq, right. So, you get 1 minus n minus 1 by m times half as claimed. Okay, so, this is now you have a binary code with a decent distance. So, if you take the field to be, let us say 10 times n, so you stretch 10 times, okay, then this distance is very close to half. So, let us do that analysis. What is it that we are getting in the end with the concatenated code? Okay, let us do some parameter chasing. So, by the prime number theorem, Why the prime number theorem? Well, because you want to work in a finite field, right? So you can work with a prime field, and for that you need the distribution of primes. How many prime fields are there actually? So we know by the prime number theorem that there are a lot of primes. In fact, no matter what k you pick, there exists a prime p in the interval 10k to 11k. Okay, there is always a prime between 10k and 11k. So let's work over the field this prime field, okay, mod p, integers mod p. So this is kind of setting your m. Your m is around 10k, and I'll think of k as n. Okay, so the field is 10 times n. Now let us go through the concatenated code analysis or parameters specific to this prime. So the concatenated code WHRS on Reed-Solomon is an error correcting code that stretches k log k long message to length. So it will stretch it to length so let me not get into the exact constants. Let me keep this part approximate. Okay, stretches around k log k long message to length m times q in the previous notation. M here is kind of p, so I take this 10k. And log k will be stretched to k. Well, log k will be stretched to p. And yeah, okay, let's not be too precise. So say this is length around 10k times 11k. That's the upper bound. Okay, order k square basically. So by the previous analysis on the concatenated code, k log k is being stretched to around k square. And the finite field that we have picked is this prime field. P is a prime number between 10k to 11k. And the distance is so what is the distance parameter? So that is half times 1 minus n by m, right? So n is, we are taking it to be k, and m we are taking to be the prime p, which is 10k. So this means 0.45. Right, so distance is 45%. So the error that this concatenated code can, and it's a binary code, that it can handle is half of this. So which is more than 22%. So let's note that down. That's our important observation. It is important especially for in practice, for practical applications, right? So for all numbers n, there exists a polytime computable error correcting code E which will stretch n to n square. That can sustain 22% of errors. So, there is a error correcting code which is polytime computable in the message length. It stretches to around quadratic. In fact, it stretches to less than quadratic because it is stretching k log k to k square, right. It is less than quadratic, it is sub-quadratic stretch. And most importantly, the errors that it can handle is 22%. Okay, so by handle we mean that even if there are 22% errors in the channel of communication, the corrupted code word will have a unique message string. Okay. There will be a unique code word that will be close to corrupted code word. So, this is an amazing property. When we started this problem, we had no idea that such a thing exists, right, because the key thing here is polytime computable. It's a really efficient error correcting code, and it is able to handle, at least theoretically, a large fraction of errors under sub-quadratic stretch. So, the question now is all this is good theoretically, but to be actually useful there should be a decoding algorithm. Right now the decoding algorithm seems to be just go over all the code words and find the one which is closest to your corrupted code word, but that clearly is very inefficient. The space is just too huge to search for in practice. So, we need a fast decoder as well. So, how do you do efficient decoding? That is the question. So, can we find the unique X given a corrupted code word or given a string y prime close to the code word EX? So, you want to find the unique X such that the code word corresponding to X, E of X, E is our error correcting code. When you send over the channel, it will get corrupted to Y prime, but it will not be too corrupted, it will be close to, in terms of Hamming distance, it will be close to EX. So, given Y prime, can you find X? That is the question. So, decoding Walsh-Hadamard is trivial. Because Walsh-Hadamard is already such a long code, 2 raised to n length, that in that much time you can go over the whole space and find X. So, since the length is 2 raised to n already, we can afford to scan the whole space . 0 1 to the n. and find the unique x. Given y prime in poly 2n time. Right, this is a simple algorithm, just search the whole space. This is, we call this efficient or fast because the length was already exponential, right. So, in terms of that, this is polynomial time. A more interesting challenge will be the question how to decode Reed-Solomon and then Reed-Muller, and finally the concatenated code. So, decoding Reed-Solomon. So, let us fix the question clearly, what are we given and what do we want to find. So, you are given a list of evaluations, right, m evaluations of a polynomial is what you are given. So, a1 b1 to am bm, you are given for which there exists a degree d polynomial g such that g's evaluation at ai is bi. And remember that g is unique as well. So, let me write that here, for which there exists unique polynomial such that GAI is BI for T of the pairs. So, it is not that GAI is equal to BI for all the pairs, for all I, right. That is that would be the case when there is no corruption that happened to the code word which was sent over the channel. So, obviously, in reality there will be corruption, maybe 22% of the pairs are corrupted. So, it is only the remaining 80% or 78% of the i's for which GAI is equal to BI, and from this you want to compute or find G. Now, since RS has Reed-Solomon has distance 1 minus d by m, right. Remember G is degree d. So, since Reed-Solomon has distance this much, we are guaranteed the existence of a unique G if T is big enough, right. T should be m minus the errors that you can tolerate, which is half of d by m, which is m plus d by 2. and the field size, which is M, this should be bigger than the degree. It is an interpolation question, so obviously you should have enough field elements, otherwise you cannot interpolate a d degree polynomial. So remember these two parameters, that t is more than m plus d by 2 and m is more than d. So in particular t is more than d. So that sanity check is passed. I mean, you should have more than d pairs where g is correct, evaluation of g is correct. Otherwise you cannot hope, it's impossible to get a degree d polynomial g. But we want to give an algorithm to find g, and the problem we are facing is that we don't know the i's, which i's are correct, which i's are bad, right. So the number of subsets of M is too large, we cannot go over all possibilities. So how do we solve this problem algorithmically? Well, if T was M, that is everything is correct, then we can just use interpolation. We could have just interpolated G from the linear system. GAI equal to BI for all I 1 to M, right. So if there is no error, then this is just an interpolation problem, you can solve it, you can find G. But what if T is less than M? Okay, so we will do that now. So assume that T is smaller than M, which means that M minus T pairs are erroneous and you don't know which pairs are good, which pairs are bad. Still you want to find G. So the idea is in this case to compensate for the errors, you introduce an error locator polynomial. Which is called the error locator polynomial. We will call it EX, which has degree equal to number of errors, and number of errors you know can be M minus D by 2. Now obviously we don't know which pairs are bad, which AIs are bad or BIs are bad. So we will also not know the details of this error locator polynomial, but we can set up an equation. So interpolate or find C and E from the following equation: CAI equal to BI times EAI. Now since we don't know which i's are good or which are bad, we have to treat all of them equally. So set up this equation CAI equal to BI times EAI for all I. This gives you across all i's you have now m constraints, where degree of E is already set to m minus d by 2, and degree of C is supposed to mimic G. Okay, so the degree of that is, well, okay, no, now C will mimic something like G times E. Okay, so this will be degree of G times E. So that degree will be D plus m minus d by 2. Which is equal to m plus d by 2. Okay. M plus d by 2 has another importance. You know that T is bigger than this. So now you can see that the number of places where AI comma BI pairs are correct is more than the degree of this system. Okay, so there is some hope. And so when you solve this linear system, you will get very useful information. So that is how people came up with Reed-Solomon decoding. Okay, so let's make it a theorem. So this is due to Berlekamp and Welch. They showed that there exists a polynomial time which is polynomial in m and log of the field size. The field size you always assume bigger than m, which is bigger than n, right? But this is truly polynomial time. In this much time, deterministic polynomial time, this algorithm, there exists polytime algorithm to find G from AI BI. So whatever this data is, with the guarantee that T of them are correct, T of the pairs are correct, you can find G. So the algorithm is as follows. So first step is find polynomials Cx, Ex of degrees m plus d by 2 comma m minus d by 2 respectively, such that for all I, CAI is equal to BI times EAI. Note that this is a linear system. So from the linear system you can find a solution, right? You just need to use a linear system solver, and that will give you polynomials Cx and Ex. And then you just output. So the understanding was that C is G times E. So you just output the ratio. So output Cx by Ex. So it's a simple algorithm. It is certainly efficient, but it is not at all clear why C by E will be a polynomial, and why would this be the unique G, right? The algorithm tells you nothing about, gives you no hints. So let us try to prove that, right? Everything is in the proof actually. based on the idea that we discussed. We are thinking of E as the error locator. So, it will basically, intention is to collect these bad AIs in the error locator. So, in step 1, there are m equations and how many unknowns? So, number of unknowns is 1 plus m plus d by 2, that is for C, and 1 plus m minus d by 2, that is for E, which is m plus 2, right. So, there are m equations, m plus 2 unknowns, and it is a homogeneous linear system. So, these are linear homogeneous. So, it is possible that well, I mean, since it is linear homogeneous with many unknowns, it will always have a solution, and in fact you know one kind of solution. We already know a solution by considering, take E to be the bad AIs and C to be G times E, right. And you can see that CAI is equal to BI times EAI for all I, because for the good AIs CAI is always GAI times EAI, and you know that GAI is equal to BI for good AIs, and for the bad ones this EAI will be 0. Okay, so either EAI is 0, or when it is non-zero, then still because of GAI equal to BI this equation is satisfied. So, this equation is always satisfied, and that is the beauty of this idea. So, we already know a theoretical solution, it is a linear system, we can solve it. So, we will get some solution, maybe this one or something else. So, let C and E be the solutions obtained in step 1. The linear system solver gives you some C and E. It might not be this ideal case C and E, right. So, how do you know about C divided by E? It may not be G. So, let us see that. So, you know that for many values, for the good AIs, CAI minus GAI times EAI is equal to 0 for T of the i's. Right, this you know because for T of the i's GAI is equal to BI. So, you know that whatever the solution C and D are, they will satisfy this at least for T of the i's, and for all of them they satisfy CAI equal to BI times EAI. Now, note that if you look at the degree of CX minus GX times EX, this degree is, well, Cx is degree m plus d by 2 and G times E is also the same. So, it is at most m plus d by 2. and we have taken t to be larger than that, right? What t did we take? Right, greater than m plus d by 2. So, degree of c minus g times c is smaller than t, but the above statement in blue says that this polynomial vanishes for t of the i's, which means that this polynomial is 0. And that's so this is the proof. This finishes the proof, right? This is the reason why no matter what C and E you get in step 1, C by E is always G. And that is what you output in step 2. So, all steps are doable in polynomial in M, which is basically the degrees involved, and the field, log of the finite field size. You can do addition, multiplication, and also division, right? All these field operations, ring operations can be done in polynomial time. So, this finishes the decoder of Berlekamp-Welch for the Reed-Solomon code. Okay, this is one of the nicest algorithms in algebra, and this is what we will build on as we move forward to more complicated encodings. So, let us now immediately apply this to decoding concatenated code, right? Walsh-Hadamard on Reed-Solomon. So, for Walsh-Hadamard Reed-Solomon code, which is basically this map n log q to mq bits, there exists a polynomial in the finite field, right? So, this is the size of the field. Size of the field is an upper bound on both n and m. So, there exists a polynomial in q time decoder if the fraction of errors if the error fraction is less than half of the distance, which is, it has to be actually half for each of these. So, for Reed-Solomon you have to halve, which will give you half minus n minus 1 by 2m, and then on top of this Walsh-Hadamard also you have to halve, which will be half of half, which is 1/4. Okay, so it's kind of 1/4 of Reed-Solomon. So, for our parameters, when Reed-Solomon was handling 22%, this will handle 5%, slightly more than 5%. So, let y prime be close to y, which is a concatenated code word, right? So, that is Walsh-Hadamard on Reed-Solomon symbol, ith symbol for all I. And y prime distance to y is as given above, the error fraction. In that sense, it's close. So there is some corruption, let's say up to 5% corruption. Now the hypothesis on this error fraction implies that number of symbols, ith symbol I, such that Walsh-Hadamard on the symbol has a lot of errors, okay, at least q by 4 errors. Number of such i's cannot be large. The reason is that if it is large and Walsh-Hadamard in each Walsh-Hadamard of the symbol, the errors are also large, then overall it will exceed the bound that the hypothesis has put. Okay, so by averaging, basically you are getting that the number of symbols on which Walsh-Hadamard is making a lot of mistakes is smaller than half minus n minus 1 by 2m times m. Okay, so that's giving you m minus n plus 1 by 2. So the Walsh-Hadamard encoding of at most these many symbols has a lot of errors in the code in those symbols. So the remaining cases, Walsh-Hadamard of the symbol has fewer than q by 4 errors, and that is where you then do Walsh-Hadamard decoding. So Walsh-Hadamard decoding will yield m tuple which we will call y tilde, where basically more than half of the cases yi tilde is correct. So locally you have decoded using the Walsh-Hadamard WH decoder, and more than half of these are correct values. You will not know this, but it's a guarantee that WH decoder gives you. You won't know which i's are good, okay, but you will know the number of i's that are good. So with yi tilde equal to correct ith symbol for greater than m minus n plus 1 by 2, which is m plus n minus 1 by 2 of the i's. You don't know which ones, but you know the number of i's. It's more than m plus n minus 1 by 2. So after this WH decoder, now you have symbols where a lot of the symbols are correct. You don't know where they are located, but the guarantee is many of them are correct. And at this point you should invoke the RS decoder, right? That will give you X. So RS decoding of y tilde yields the unique X. Right, because RS decoder needs how how many correct i's? More than m plus degree by 2, and in this case degree is n minus 1, right. So, it is more than m plus d by 2 by the previous RS decoder. So, what we have learnt is Walsh, Hadamard, Reed, Solomon is a practical binary. It is both binary and a linear error correcting code that encoding decoding both are polynomial time, and it handles up to. So, for Reed Solomon, what did you learn before? That it can handle 22% of errors, right. So, let us just do 1/4 of that. So, 5.5% of errors. So, if there are 5% of errors in the channel, then you can use Walsh, Hadamard, Reed Solomon coding. So, all these are beautiful results, both theoretically and practically they are very nice and in a way unexpected also. Now, remember our goal was to do amplification of function hardness, right. So, for that, as we alluded before, not just decoding, but stronger forms of decoding will be required. So, the first form that I will define, stronger form of decoding, is local decoding. So, recall that for hardness amplification, we need stronger forms of decoding So, the next type of decoding concept is local decoding. So, we will define the concept. It is basically that you will be allowed only to query the code word or the corrupted code word string in few places, and from those few places when you query the bits, you have to guess let us say the first bit of x. Okay, so, the goal is not to find the whole x, but first bit of x, and in the code word or corrupted code word you are allowed only few locations to query. So, we will define it and then we will actually do it for these 3 or 4 coding mechanisms that you have seen in the next class.